Chapter 9 of Astrophysics. We are covering galaxy clusters and dark matter. The image that you see here is a galaxy cluster IDCS 1426, and that blue haze that you see is from X-ray observations showing very hot gas that fills a large amount of the mass of the entire cluster of galaxies, but we'll get to that later. All right, first of all, what is a galaxy cluster? Well, we can start with our local group of galaxies that includes the Milky Way, and this diagram on the upper left is centered on the Milky Way, and there are many small dwarf galaxies that are labeled in green, and they have a much smaller mass than the Milky Way, but there are two other galaxies in this local group of a similar size. Andromeda is a very similar size to the Milky Way, and there's also Triangulum, which is about 20 times less massive and about 3 times smaller in size than the Milky Way. And this is a group. Usually that refers to smaller groupings of galaxies. For a larger group, these are known as clusters. And shown on the bottom right is the Abell 2744 galaxy cluster. And you can see quite a large number of galaxies. Some of them show a very nice spiral shape. Others, and actually the majority of them that you see in the center region, are ellipticals. And what we see for these large galaxy clusters that can hold over 1,000 galaxies is that in the central region, it is mostly large ellipticals. And in fact, there's often at the very center a very large elliptical. And the closest galaxy cluster that we're actually a part of is the Virgo cluster. And that includes M87, which is a very large elliptical galaxy at its center. I should say that we are part of the supercluster with Virgo, so that clusters can even group together. Okay, now similar to an elliptical galaxy, galaxy clusters show orbits that are random in terms of their direction, and often they can be very non-circular and may not really even be in fact an orbit. So we have much more random motion inside of an elliptical galaxy. That's the stars that have this motion. Here we're talking about a cluster, and each of these moving objects is a galaxy itself. So what can we measure with a telescope? Well, we can measure along our line of sight, and we get a spectral line. If we look then, if that line is shifted, we get the velocity either away or towards us using the Doppler shift. So this is known as the radial velocity along the radial direction. And we can measure those for the different galaxies. If you take the average of those radial velocities, what you get is the average speed that the entire cluster is either moving towards or away from the Earth. And in fact, we'll find out that it's always away from the Earth, the Hubble's law that we saw earlier when we introduced galaxies. So that's fine, but what we want to do is actually look at the relative speed that these galaxies have relative to the cluster and not relative to the Earth, so relative to that center of mass in the cluster. So what we need to do then is define a radial velocity relative to the cluster's rest frame, which we'll call V parallel, and that's just a notation reminding us that this is along our line of sight. And for a particular galaxy, we'll call it I is the galaxy. I'll use the subscript R to remind us that this is what we've measured for that particular galaxy in the radial direction, and we are subtracting the average of the radial velocities for all the known galaxies in that cluster. So in other words, we're just subtracting the average speed. Now, looking at the bottom right, we see a reminder that we live in three-dimensional space and that the velocity has x, y, and z components, and we're only talking about one direction. So if we line up, for example, the z direction with the Earth to the cluster, then that's only one of the three perpendicular directions. If we use Pythagorean's theorem, then we can relate how the components are related to each other. So we have the total velocity squared is the x component squared plus the y component squared plus the z component squared. Okay? And that's fine, but what we have is a large population of galaxies, so we're looking at the average components. And in that case, then we have these average values that also follow the same relationship. But notice I've put bar on top to show that these are the average along these directions. Okay, now this simplifies a bit because we're using average values, and since the motion is randomly orientated, then it's equally likely that a galaxy is moving towards the x, the y, or the z direction. And so we can then say that these components squared are equal to each other. In other words, x squared is equal to y squared is equal to z squared. So again, we choose, and this is for the average. Remember, this is the average value. So we said that this could be, if we're looking in the z direction, then we have the v parallel as the z, and that's squared. And that's the same as the other two, so when you add them up, you get 3 times that. And that's very useful because now we can think about how do we measure this. So we said that we're measuring these radial components and we can get an average. And this average of the v parallel squared is a variance. It's equal to sigma squared because that, we'll see that the definition of the variance is exactly what we're calculating. So 1 over n, the number of galaxies here, is multiplied by the sum over this subtracted velocity, and that thing's squared. So we see that that term in the brackets is just v parallel, and when we take the average of that, well, we first square it, and then we add up those, and then we divide by the total number n. So we now have something that we can measure, which is this sigma squared. And sigma is normally known as the dispersion. It's just another word for this spread in these velocities around the average. And we can now insert that into an average kinetic energy. So average kinetic energy for a galaxy is 1/2 m v bar squared, where m is the mass of the galaxy. And if we now look at our formula where we had v bar squared, we said that's equal to 3 times sigma squared. So we can just now substitute that in. So we have 1/2 m times 3 sigma squared. Okay, excellent. We are now going to use the virial theorem. It's a little bit different than the virial theorem we saw previously, but it's the same idea that, I'll write this out, virial theorem. If I can spell, sorry, that's an O in there, is generally that this average kinetic energy is equal to a minus 1/2 of the average potential energy, where U is the potential energy, and we can substitute in what this average potential energy is. So we have minus GMM. Big M is now a mass, that's the total mass of all of the other galaxies relative to this mass that we're sort of considering. And this is a little bit rough, but this works for an average, where little m is the average mass of one of these galaxies, and capital R is an average separation between a galaxy and the center of mass of this whole system, this cluster. So we know what K bar is. It's something that we can just put in here. So that's 3/2 m sigma squared. Okay, and if we now can solve for capital M, because the little m's cancel, we can find a way to get the measure of the total mass of this galaxy cluster. Because we've measured sigma squared, we can approximate what R is just by looking at the image that you get for a galaxy cluster, and G is the gravitational constant. So this formula gives us this estimate for the entire mass of the galaxy cluster. If we put in some typical values, that sigma is quite large, it's about 1,000 kilometers per second. The cluster size is quite large. This average value is something like 0.5 megaparsecs, which could be roughly half the size of the entire galaxy cluster. And if you plug all that in, you get something like 10 to the 14 or 10 to the 15 solar masses for the total mass of the galaxy cluster. The interesting thing is that that is not the same mass that you would get by just adding up the expected mass of each of the individual galaxies. So if there's, say, 100 or even 500 galaxies, and you estimate that each of them has a mass of 10 to the 11 or 10 to the 12 solar masses, you multiply that together, and you still don't add up to this total amount. You would get, say, 10 to the 14, and you would actually be on the very lower end. And what we'll see is that there's a lot of mass in these clusters